Hello everyone, this is the video lecture for Business Calculus Math 1325 section 11.6. We're doing optimization. So we're optimizing different functions. This is going to be super fun. I really like some of these applications. It's really cool. And then there's one at the end that I hate. But anyways, the rest are great. So, but that's how it often is, you know what I mean? Think about your job that you're going to have or you might already have now. Is it always the most fun thing ever? No, it's not. But that's okay. That's why we're going to get through this together. So I'm just writing some words, by the way. Your audio is not having a desynchronization problem or something like that. It's just I'm writing while I'm talking. And then I'll explain what I'm writing here in just a minute. So, bloop. Okay. So find mins and maxes, mostly word problems, and find the first derivative, set it equal to 0. You're going to also test the endpoints as well, etc. There's nothing new here. The math is not new, but I think that these problems are new because, oh boy, here we go. 11, 6, 9. These are some classics, and they're word problems. Here we go. Find two numbers whose sum is 19. Yeah, you can skip ahead, by the way. Is 19. That does not look like a very good 9. Okay. And whose product is a maximum. Okay, this is a classic. I love this kind of problem. We're going to have a lot of these as we keep going. So what does it mean? Two numbers whose sum is this but product is that. So you're going to have x plus y. You're summing them, meaning plus, is equal to 19. And those same two numbers, x times y, product, is equal to a maximum. What the maximum means is that my derivative was equal to 0, essentially. So I'm going to put an arrow because it's not equal to that. But your derivative is equal to 0 at that point somehow, blah, 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 blah. Okay, so how do we do this? I went and started doing some crazy math, and it was fun. And I got it all wrong. So let me show you the right way as opposed to the first time, okay? So here's a better setup. I got x plus y is equal to 19, and then I got xy, as multiplying them, right? Xy and then prime is equal to 0, okay? So I'm going to solve. I'm going to take this top one. I'm going to solve. So I'm going to let's solve for y. That way I can start doing x's and stuff. So y is equal to 19 minus x. And then I can plug that in here. So I got x times 19 minus x, and then all prime is equal to 0. It's way better to just distribute that. Oops. Distribute and not write it. There you go. I keep putting a prime because I need to find the derivative of this thing. And I can. It's 19 minus 2x. I mean, you see how that works, right? I simplified it, and then I did my derivative, and now all I need to do is start solving. So 19 is equal to 2x. Divide by the 2 on both sides. So x is equal to 9.5. And what's interesting is that I need to now plug that in to my y equals. So 19 minus 9.5 is 9.5. So they're actually the same numbers. And there's a trick, a hint here, which I didn't want to just tell you. So it says two numbers whose sum is this and whose product is that. Now, this is a little bit higher math, but the sum, the addition, and the product, the multiply, so plus and multiply, are both commutative. And this is some high math, definitely not business math kind of talk. But I want to tell you because, well, you're listening, and there you go. So it's commutative. Basically, what I'm saying is 2 plus 3 is the same as saying 3 plus 2. That's all it's trying to say, is that you can swap them and it would be the same. Or I could say like 2 times 3 is the same as saying 3 times 2, and that's good. So that is the commutative property. But now imagine 2 minus 3 is not equal to 3 minus 2. You see how those are not the same? Same with the division. It's not going to work. So multiply and addition, so addition and multiply are commutative, and this is special because basically these two numbers here that they're saying are ambiguous. They're ambiguous. And what meaning behind that is that they didn't say that the first number was different than the second one, essentially. And there was no reason for me to think that one was different than another. And in this particular case, because they're both ambiguous and we have the commutative property of blah, 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 you're going to get the same number. So all that long-windedness to just say, if you got one, you can just go get the other one. Or, even better, in the future, you could have just simply said right here, 2x is equal to 19 immediately. Like, you didn't have to go and solve for it down here. I'm just saying, like, you have x and you have x because they're the same thing. It's an ambiguous number. Therefore, you could just say times 2. Divide by 2 on both sides. And there's your 9.5. We're done. We didn't have to do any of this math. Okay? It's kind of a weird setup. That's not something I would say for you at this point to rely on. This is business calculus. You're not going to always see that. But that is some theory to some reasoning why we can do these things. And watch the next one. You're going to be surprised. You're not going to be surprised. You're not surprised. So find two positive numbers. Two positive numbers whose product, can't spell product today, product is 253, and the sum is a minimum. It's a very similar problem to the last one. Product, sum. They're both commutative. Therefore, these two positive numbers are ambiguous. I'm wanting to say like x times y is equal to 253, and that x plus y is equal to a minimum. And we're going to do some math. Awesome. But because they're both commutative, because they're ambiguous, in a way here, I'm expecting them to be x squared is equal to 253. Square root both sides. And you're done. That is quite literally what they have for the answer. I'm not kidding you. And they do want you to use the square roots in this particular case, just as a technical thing. You can see that, like, if you kind of understand some of these properties, you're done. You don't have to do any math. Now, I'm going to do the math with you because I love doing the math. It's just fun. But here we go. So I'm going to solve for y and then plug it back in. So my y is equal to 253 over x. And I'm going to plug that back in. So I got x plus 253 over x prime is equal to 0. Okay, so when I take derivative, that turns into a 1. Because this is a negative 1 power, I'm going to bring it to the front. Now it has a negative 2 power. I'm going to move this over just because it's negative. But essentially, I have 253 over x squared. If I swap, well, if I just multiply that over there, I don't have to swap anything. Square root both sides, plus or minus. But because it said positive numbers, then we don't need that negative. It's just positive. Positive only. Okay? Hey, look at that. And then you can plug it back in and you'll get the same thing. You know what? I'm going to even plug it in. I'm even going to plug it in. So my y is 253 over the square root of 253. So because of the radicals in the bottom, you pop it in the top and leave the number behind. Oh, they cancel. Look at that. So, I don't know. It's a pretty cool thing. I just wanted to point that out to you because I think it's cool. And definitely it can be fast. And so you learned a little bit of math theory as well. Okay, so I got a little p, which means price, and then I got a capital C, which means cost. Okay, and they're looking for maximize revenue. They want you to maximize the revenue. Like basically x equals what? Okay, so first off, we need to know what revenue is. Well, here's a formula for revenue. It's x times p. So why is the cost in there? Oh, it continues. This is only part A. Okay. I was like, has nothing to do with cost. Why is that in there? It's only part A. It's fine. Okay, so x times p. And so I would say x times the 400 minus 0.5x. And I'm going to distribute that x. So 400x minus 0.5x squared. And to find the maximum, I'm going to say my derivative equals 0. And so my derivative, r prime, would be 400 minus, and the 2 comes down to the front, 2 times a half x. These cancel, leaving just a plain x. And then you set that equal to 0. Solve for x, 400. There you go. And they don't want just that. They also want, like, what is the price at 400? And so that's when you plug in 400 minus 0.5 times 400, and you're going to get 200. Again, I'm just plugging it into the price right here. I'm just plugging that in right there, okay? Cool. So that's what they're wanting for, like, part A. I didn't write it down perfectly. Just it was something like that. And so now we're going on. Oh, no. So now they want to maximize the revenue, which we already did at 400, but they want like the actual R of 400. And so then we're going to go 400 times 400 minus 0.5 times 400. That's a lot of 400s. And the answer is 80,000. That's like dollars. I guess that this is dollars also. Cool. Okay, so now part B, finally. Oof. So now they're saying find the maximum profit. So this is actually going to be a whole different problem. Let's just talk about it. I think the theory here is pretty cool, right? So they said find the maximum revenue. If you had no concept of what the cost was, you were just wanting to know the price and how much to sell it and all that kind of stuff, then we are done. We did it. But because there's always a cost involved, we're now needing to go to profit to equalize it in a way. So profit is equal to revenue minus cost. And so long-wise, it's x times the 400 minus 0.5x. Minus the cost is the 15,000 business plus 130x. So there's your revenue minus cost is what that is. So there's my full profit function. So of course I want to simplify. I'm going to distribute this minus sign as well. And so I got 400x minus 0.5x squared minus the 15,000 minus 130x. Combine like terms. Positive 270, like these guys right here, like at the ends. And then minus the 1,500. Cool. So that's my profit. And now I'm going to do prime. So my derivative. When the 2 comes down, the 2.5 cancel, make a 1. So I can just do that if you're okay with that. I'm going to set it equal to 0. Move the x over. 270. So 270 is my units, I guess you can say. And so they're wanting what's the price of at 270. And like, yeah, I could be using calculator, but I already have the answers, so I'm sorry. So 400 minus 0.5 times the 270 is 265. And then they want to know what is the actual profit at 270. And so then we're just plugging it in to right here. Let me go ahead and rewrite that. Oops. Okay, so I'm plugging it all in, and I'm just going to give you the answer. It's 21,450. There you go. Whew. All right, good enough. So that's the end of that problem. We got more. So I got a cardboard thing. Got a fence, rectangular fence we're going to talk about. And then bandages. It's only 3 problems left. So here we go. 11, 6, 31. Cardboard cutout. So it's kind of like a cardboard box. And it's 21 inches by 12 inches. Okay. And they want squares of equal size to be cut out of the corners. So squares of equal size cut out of the 4 corners. I'll show you a picture here in a second. They're going to fold to make a rectangular box. Fold to make rectangular box. They say, what is the maximum volume? Okay, I know you're business folk. This sounds like an engineering problem. It's not. It's not. I mean, yeah, I guess if you want to make it an engineering problem, it's fine, but it's not. Because you might need to make a box to sell things, and we're trying to fill it up with the most marbles or, I don't know, pins or whatever you're going to be putting in there. And I know that you're not going to do the math on this. You're just going to probably just do it. But, I mean, the math is important, okay? And maybe it's like in a high production run and you're wanting to know, like, well, I'm going to be making like 10,000 of these items. So let's try to make this the best that we can. So here we go. What's going on? We have a piece of cardboard that is 12 here and 21 right there, okay? We're going to cut out a square from the 4 corners. So like these are going to be gone. I'm just going to like scribble on them if that's okay. They're going to be gone. And then we're going to fold this thing along these edges here. And it'll fold up to be a box like this. And it'll be a little longer on that side right there. There you go. So, well, I guess you'll see it like that. There. Perspective and stuff. Anyways, so there's your box, and then you fill it full of stuff, and it's cool. So this is your 12. It's not 12 anymore. Whatever that is, I don't know what that is. Let's call this, we have to give it something, right? How about this? We have to like, because we're going to now need to find out what distances these are. Let's see let's call these X. Let's call that X, okay? So that's a little square that we're cutting out of the corners, and then we're going to fold it up and then tape it and stuff. Here's your tape, a little piece of tape here. There you go. And then it's holding it all together. Anyways. So yeah, those are X. Okay, so we want to find the volume. And volume is it's width times length times height. Right? I mean, basically. Or length times length, or width times length times depth, or something like that. So how are we going to do this thing? So my width is going to be the long one. Let's call this one here the width, okay, the longer side. So how that works is that it was originally 21, but I'm cutting out 2 of these x's. And so I would say that's 21 minus 2 x's. And this one right here, I'm going to call this my length or whatever. I don't really know. It doesn't matter. I have my 12, but then again, I'm removing 2 x's. I'm removing this one. I'm removing that one. So this length here is not 12 anymore. It's 12 minus the 2x, okay? And then the height is however much I'm cutting it out. So that's going to be height of x. So here we go. I got 21 minus 2x. I got 12 minus 2x. And then I have an x. And they're multiplying the whole thing there. And this is supposed to be a maximum. Okay. Time to start foiling. So I'm going to foil this thing out like this. Here we go. So 21 times 12. Pause. I'll use my calculator this time. 252. And then I got 21 times 2 is a 42x. 2 times 12 is 24x. And then 2 times 2 is 4. Those two negatives make a positive. And then all of this is still times x on the outside. Distribute your x into everything here. Combine these like terms. So let's do that. Let's do 42 and 24, like a 66. So now I've got 252x minus 66x squared. And then I got 4x cubed. I'm saying this is a maximum. Okay. In order to find then, that's my volume. And so I'm going to do v prime is equal to 0. And so here we go. I'm going to do 252. The 2 comes down to make it 130 something. Yeah, 132 x. And then the 3 comes down to make it a 12x squared. And now this is set equal to 0. What do they all have in common? I really hope it's a 12. So 252 divided by 12 and 132 divided by 12. Sweet. So I could take a 12 out of each one of these. Okay, that's better. And then I want to factor that. What two numbers multiply and add? 7 and 3? No, actually. 7 and 3 make a 10. Well, darn. If you can't factor it, what do? You don't need that 12, by the way. What do? Quadratic formula. Oh, no. Chad, why? Hi, my name's Chad. Okay. So, quadratic formula. We've done this. I'm hoping you've done this a lot. I guess you could do, that's what, 40, 80, 84, 84. I guess you could use your calculator, Desmos, graphing in particular. And I'll show you that here in a second. I don't want to leave you hanging, right? But I got to have fun too. Okay, so those are answers. And of course, those are the most awesomest answers ever. So let's do 11 plus the square root of 37 all over 2. And 11 minus the square root of 37 all over 2. And let me write down those x values. So we got x is equal to 8.5413. I got 2.4586. Okay, awesome. So those are the two answers I just got from the calculator. And I'm going to say only one of them work. And so let's go back for a second. Remember that we had 21 and 12. And I'm saying that this distance here is that x, okay? This is that distance x. So what if I had an 8? I'm saying that this distance here is an 8, and this distance here is an 8. But if you look at it, it doesn't make any sense. Because this whole distance here is 12. And you got an 8 and an 8. So what it does is it's overlapping. It's like you got 8, and then you got an 8. Okay, that was terrible. Let me try that over again. So you got 8, and you got 8. And it's overlapping. Can you cut this portion out twice maybe? No. So the 8 is actually too much. The answer then has to be the 2. So you're cutting out a 2 and a 2, and then leaving about 10, 9.5, 10, or whatever it's going to be. And boom, there you go. That's how you would find the maximum. And that's the answer, by the way. This is what they want for the answer. Could I have done all this in Desmos graphing somehow? Probably. So let's do right here, this volume. Like basically I just said, what's the problem? And I drew a picture and I did, well, this is my volume. Scroll out. Okay. You see this right here, this point right there? There it is. 2.4 whatever. Didn't I just get that? There it is, see? Okay, well that was pretty easy. Now you know what to do. Okay, fences. Oh, I'm so stuck on twos. 11, 6, 33. So there's a fence of a rectangular area is 1,800 square feet, okay? And it says 3 sides, cost $3 per foot. The last side costs $9 per foot. Okay. So what's the most economical fence? Okay. This is a pretty cool problem, honestly. I know you're thinking it's another mathy, weird engineering kind of problem, but these kind of things happen in business all the time. The classic one is that there's like a river and you want to like do it in 3. So you do 3 different sides, but not the last one. That's not this case, but it's something similar. So let's say, imagine there's a river and you're trying to do this, and that sounds great, but the fence, you still have a fence that you need to put on the river because otherwise they'll just walk around it because that's what cows do. So you still need a fence there, but because it's so close to the river, it needs to be like super reinforced and all that stuff. And so these are the $3 fences. It's just like the regular T-posts and stuff like that. $3. But this is the high dollar, like water resistant something blah blah $9 fence. Okay, so something kind of like that is going on. Now they don't specify this is like longer. It could be shorter. So again, it's one of those ambiguous cases where it could be something kind of like this. And so then this is the $9, and then we got $3, $3, $3, that kind of thing. They don't say. Anyways, so that's what we're looking at, is something like that. So I'm just going to make something up. Let's say it's X and Y. Or again, you could do a vertical one. Something like this, which is probably what it's actually going to end up looking like. It's going to be something like this. So this one's probably the real one. If you're going to choose the 9 to be that guy, that's up to you. I'm going to choose, I'm not going to do this route. I'm going to go this route here and say this is my $9 fence. But then the other is going to be $3, $3, and $3. Okay, so it's however you need it. I'm just going to choose this one because you have to choose something. Okay, so that's what it kind of looks like. Here's a river. There you go. All right, awesome. So with this in mind, we need to find what our cost is going to be. So my cost is going to be $3 for this one, this one, this one. So that's 2 X's and a single Y. Oops, $3. And then plus, I'm going to have a $9 fence for just the single 1 Y right there. That's a Y. It's a little bit sloppy. So that's my cost. And if you distribute the 3 and basically the 9, you got 6x plus 3y plus another 9y. 6x, combine like terms, you get 12y. So that's my cost. Okay, cool. But now the area, if you remember, they actually specified how much area we need. It said right here the area's got to be this much, like exactly. So that would be 1,800. But how do I find the area is length times width, x times y. Cool. So basically what we have here is my cost is supposed to be minimum. and we have an area that's fixed right there. And these two equations we're going to be putting together in order to find out what my answer is. Now, could I just go to Desmos graphing for this immediately right now? Honestly, I don't think so. I would not. I would say that there is a little bit more work to do, and then you could probably use some Desmos, but in the meantime, here we go. I'm going to solve for y, so I'm going to divide by x on both sides, so I get the 1800 divided by x, and that's what I'm going to plug in right there. So then I got 6 times, no, I'm going to plug it in right there. I'm so sorry. So I got 6x plus the 12 times this stuff is equal to the minimum. I was wanting to say the 1800, but that's not the case. It's the minimum. I did it again. That's not a y, it's an x. Bad Chad. Here, can I erase this? Okay, awesome. Yeah, that's great. Okay, that's an x. Okay, so 12 times 1800. Let's go back to the calculator for that guy. Yep. So let's write it out. So I got 6x plus 21600 all divided by x is equal to my minimum. Okay. Sweet. All right, so how do we do this thing? I'm going to just start finding my derivative. So minimum is derivative equals 0, that kind of thing. So let's do our derivative. So I got a 6. Remember that this one here is a negative 1 power, and I'm just going to have to remind you about that. It looks like this. So you bring the negative to the front, leave the number alone, and then now it's going to be divided by the square version. And now, because that was the derivative, I'm going to set it equal to 0. All right. So let's do this thing. This is a big fraction, and I'm going to move this over to the other side just because it's negative. And I'm going to multiply here and divide by this. X squared is equal to 21600 divided by the 6. Let's find out what that number is, because I want something a little bit easier. Oh, okay, cool. That sounds great. 3600. Square root both sides. And I think it's just going to be a 60, but let's just verify it just in case. Oh, yeah. Okay. So x is equal to 60. I can go back and plug it in for my y. If you remember, I have my y equals right here, 1800 divided by x. 1800 divided by 60. It's 30. Okay. And well, that's it actually. That was the end of the problem. Yay, we did it. I don't know if they have like x and y literally, or if they have some kind of like the smaller side and bigger side or something like that. I don't know. There's your two answers, 60 and 30. Okay. The last one is 11,637, and it's the bandage problem. But here's the thing with the bandage problem. It's a problem. Bandage problem. I'm gonna read it. I'm not gonna write it. I'm gonna read it. So it says demand of 80,000 bandages, $20 to store one box of bandages for 1 year, $500 for setup production. How many times a year to produce to minimize cost? Okay, so like I read this problem many times. I truly did. And it said demand of this many bandages for like a year or something, but you could store a box for a year. So why are you not doing that? And then you need to set up to make more Band-Aids. And then after that you stop. And it was so confusing. I went through the whole thing truly. I tried so very hard to make it make sense. I did like 365 days in a year, and I was like doing the bandages used per day, and I did so much work. And the answer was just something like just some random 40 or something weird. And it was very annoying, and it made no sense to begin with. And I tried very hard. I just gave up, so I deleted it. It was one of those deleting problems. Don't have very many of those, but I just had to. So there you go. And I know I wanted it to be a cool business problem about Band-Aids and stuff, but just some problems are just not great. They're just not good. So I can't subject you to that. If I can't even understand what they're trying to say, then why am I putting you through that? Okay. There you go. All right. Thank you very much. Have a great day.